Hi guys, this is Somil.
And Rishabh, I hope we're audible. You
Yeah,
could just write that in the chat if possible. Yeah,
yeah,
yeah, we're audible.
yeah.
So,
Now, okay, so I guess I'll start. We'll first be discussing greedy algorithms. So I'll share my screen. Yeah, so could Rishabh, can you confirm that that the screen is visible?
yeah, this is good.
Yeah, okay, okay. So I'll start. Yeah, so what are greedy algorithms? So, a greedy algorithm is an algorithm in which you make choices which are locally optimal according to some heuristic and try to prove that this produces a globally optimal solution. As in, if you suppose you want to find a data structure which maximizes a certain quantity, you might build up that data structure step by step in little chunks, and at each step you decide what exactly to put into that data structure based on some heuristic. So what is a heuristic? A heuristic is a guiding principle which you think a solution to the problem should follow. Often involves choosing an element which is extreme in some sense, like biggest, smallest, best, or worst. And these heuristics are the key to solving any problem greedily. Like all solutions which seem magical usually have some solid heuristics behind them which make them work. We'll be seeing examples of heuristics pretty soon, so don't worry if that just seems a bit too abstract right now. Okay, and so greedy algorithms also often involve the idea of local changes. Can you make small changes to the current configuration to move to a better neighboring configuration? In a way, you're looking at the derivative, but it isn't the derivative we learn in calculus or something in some sense, because configurations, I'll just give an example. So, what is a local change? A local change is any change which is small in some sense. For example, suppose you have an array of n numbers, say n equals 100, you have an array of 100 numbers, and you swap two elements. Suppose you swap the second and the fifth element. Then the new array you get, it is in a sense a neighbor of the previous array, because you can change one to another in by a small local change. And anyway, the change you made is local because it is pretty small. Like the array didn't change a lot. So we call such changes local changes. And so what you do in greedy algorithms often is you see how the quantity that you're trying to optimize varies when you make such local changes, which are small changes. So, and greedy algorithms are usually efficient because you only process small chunks of information at each step. You don't look at all the data you have. You look at some small amount of data and make the decision based on some guiding principle. But they don't always work, and it is due to the same reason. Because you aren't really keeping track of the whole data. You are only looking at some data. So it isn't guaranteed that it will work. And if it works, it can sometimes be hard to prove the correctness, because again you're looking only at a small amount of data. How can you ensure that it works for the whole global optimum? So yeah, this is some introduction about greedy algorithm. So now let's make all of this stuff that I talked about a little more concrete by considering the following classical example. Like you are given a set of n tasks to be performed along with the starting and ending time for each task. You are supposed to choose some k tasks out of these n tasks so that the time intervals for no two tasks intersect, and k is the maximum possible. You want to choose the maximum possible number of tasks you can choose while ensuring that no two tasks are occurring at the same time. They should have different time and non-intersecting time intervals. For example, suppose you have task A, which goes on for time second 1 and time second 2. B goes from time second 2 to time second 6. C goes from 5 to 6, and D goes from 3 to 4. then you note that you can choose tasks A, C, and D because no two of them occur at the same time, and this gives us k equal 3. And it is easy to check that you can't have k equals 4 because B intersects with any other task. So you always have k less than 4 and you can achieve k equals 3. So this is a solution of the optimization problem that we were looking at. So before we start discussing how to solve this problem, I'd like to make some definitions that will make our lives easier. So a valid selection is any selection of intervals that don't intersect with each other. Basically, we just need to find the largest valid selection of intervals. And throughout this algorithm, since we'll be solving this problem by a greedy approach, what we'll be doing is we'll have a set S, which is the set of intervals that have already been chosen. Like initially the set S will be empty, then you'll add one element into S, then you'll add another element into S, and you keep doing it until you reach the final set that you want. So we'll build up the set S one by one, and a closely related set will be T. So T is the set of intervals which aren't in S and also don't intersect any interval in S. Basically, it's the set of intervals from which you should pick the next interval. For example, I'll just show an example here. So, for example, you initially had S empty, then at that point of time, T consists of A, B, C, D because there is no element in S with which an interval can intersect. So, all elements A, B, C, D are in T. Then suppose you choose C. Then S at that point of time will contain only C, and then T won't have B because it intersects with C, but T will have A and D because they don't intersect with C and they aren't in S already. Then at next step you might add D to S. Then at that point S becomes C and D and T becomes only A. Then at the next point of time you might add A into S, at which point T becomes empty, so you can no longer make any choice, and S is what you have gotten. You can't increase the size of S anymore. So you see, S and T are these sets that keep changing. We increase the size of S one by one, and the size of T decreases. And you can keep adding elements to S as long as T is non-empty. Once T becomes empty, you can't increase the size of S anymore. Okay, so now that we have that out of the way, we have heuristic one. A heuristic, as we said before, is a guiding principle, like something that intuitively makes sense to solve the problem. Like here, the heuristic is choose the smallest interval in T and repeat until T becomes empty. And this makes sense because smaller intervals should intersect with a lesser number of other intervals. So we should be able to select more intervals in this manner. So let's see how this works for the original example we considered. So the size of initially S is 0 and T is the whole ABCD. And so the size of A is 2, size of B is 5, size of D is 2, and size of C is 2. And we want to choose the smallest interval in T. So what we'll do is we at this point we can choose any one of A, C, and D because they are all the smallest. So let's say we chose A. Then T becomes C and D because B cannot be in T because it intersects with A. Then you again choose the smallest element, and if there are two smallest elements, you just choose one randomly. So say you choose C, then T will become D and you choose D, and the algorithm has given us the optimal choice of intervals. So yeah, it works for this example. But does it work always? We'll see that it doesn't. For example, consider the following set of tasks. Here, the size of A is 3, B is 2, and the size of C is 3. According to our heuristic, we should choose B because it is the smallest. And once you choose B, T becomes empty because both A and C intersect with B. So you can no longer make any choice. So the heuristic says just choose B and go home. But we know that we could choose A and C, they don't intersect with each other, and they give us two intervals. So we'd be happier if we choose A and C. So we need to think of something else. This heuristic doesn't work. So now we come to the second heuristic. So in the counter example to the last heuristic, we saw that small intervals don't really have to have less number of intersections. For example, B was small, but still it had two intersections, while A only intersected with one interval, C only intersected with one interval. So this thing that we said that makes sense because smaller intervals should intersect with a lesser number of other intervals. It might work on average, but it won't work in every case. So we need to refine our strategy. So what we do now is, instead of relying on something like small intervals intersect with a small number of other intervals, we directly choose the element of T which intersects with the least number of other elements of T. We repeat this until T is empty. So suppose you have intervals A, B, C in T, and A intersects with B, B intersects with A and C intersects with D. So you can choose one of A and C because they both intersect with one other interval in T. However, B intersects with two intervals in T, so we won't choose that. So this is an improvement on the previous strategy because here we are directly considering the number of intersections instead of relying the smallness thing. And an important thing to note here is that at each step, the size of T is reduced as little as possible locally. Because note that suppose you choose an interval A. Yeah. Suppose you had five intervals A, B, C, D, E, and you choose an interval A and put it into S. And suppose A intersected with C and D, then the size of T will reduce by 3 because A was removed and put into S, and C and D can no longer remain in T because they intersect with A. So we see that the size of T is reduced by 1 plus the number of intersections. So to reduce the size of T as little as possible, we want to choose the interval that has as few intersections as possible. So this strategy now seems really good when you consider this because you are reducing the size of T as little as possible locally, and the you can keep building the size of S as long as T doesn't become empty. So our goal is basically to reduce the size of T as slowly as possible, and this heuristic does do that, but only locally. Like at each local step it sees key in one step what is the minimum reduction that can be done. So this is a pretty bold strategy and it works for both the cases we've considered before. Like check the last case. Okay, so A has one intersection, B has two intersections, C has one intersection. So you choose, say, A. Then B gets removed from T and T only contains C. You put C into S, then you have A and C as the selection, and it is the optimal choice. So, yeah, it works for this case. But, however, there is a slightly complicated example which will kill all hopes and dreams. So this is the example. So here all these gray bars are the intervals. Since there are too many intervals, we put more than one interval at the same level. But you get the idea. So yeah, if we run our heuristic on this test set, so this intersects with three other intervals. This intersects with four others. 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 This intersects with two others. This intersects with four others, and again four, 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 three. So we see that we should choose this interval according to our algorithm first. So S will contain this interval, and T will contain these four intervals and these four intervals because now this interval intersects with this and this interval intersects with this. So we have these eight intervals in T. So now what we do is we choose any member of this side, maybe. Like you can choose from the left or right. Suppose we choose from the left. You can choose anyone, and once you choose any member, all the other members on that side are removed from T because in this any two intervals intersect with each other. So it doesn't matter which one we choose. Suppose we choose this one, then T contains only these four intervals. These four are the only ones left. And you can choose any one of them. Suppose you choose this, and then T becomes empty at this point because this. You have S. In S, you have this interval, and this interval, and any other interval intersects these intervals. So, yeah, this is the choice you got. But you can notice that you can actually get four intervals. Like this is actually the optimal choice, as we'll see later. So we can get k equal 4, but the algorithm gave only k equals 3. So yeah, the algorithm can't work. So By now we've realized that the number of intersections might not be the right thing to consider, because the last heuristic that we had, this was kind of like the strongest thing you can do with the number of intersections. Now, like, any no simple heuristic exists based on the number of intervals, based on the number of intersections, that can be stronger than this. So we start looking at things other than the number of intersections. But note that reduce the size of t as little as possible still seems like a useful idea, because the problem is still at each stage you reduce the size of t a little, increase the size of s by 1, and do this until t becomes empty. So now we try to look at the structure of the problem a little more. So what we notice is that we can order the elements of S according to their position on the number line. Like two intervals in S lie one. If we have two intervals in S, one lies to the left of the other. So more specifically, for an interval I equals open interval a comma b, we define li, which denotes left endpoint of I to be a, and ri, that is the right endpoint of I to be b. Then we can order the elements of S as I1 less than I2 till less than Is, where the right endpoint of the jth interval lies to the left of the left endpoint of the j plus 1th interval for j greater than equal to 1 and less than s. So let me show you this here. Like, yeah, suppose you had s consisted of a and c, then a lies to the left of c, so you could make a I1 and you could make c I2. Yeah, so this is what I'm talking about. The right endpoint of a lies to the left of the left endpoint of c. Yeah, so we have that. So now we see what happens if you try to build up S so that you add I1 first, I2 next, and so on. For example, if S was ACD, you would put in A first, then D, and then C. So this is like a pretty natural thing to do. You have ordered elements, you put in the smallest element first, then you put in the next element, and so on. So we see what happens if we try to build up S this way. Put I1 first, I2 next, so on. So one thing to note is that if you built S up to IM, then T can be taken to be just the set of all intervals J which satisfy Lj greater than equal to RIM. That means we only need to consider intervals for which the left endpoint lies to the right of the right endpoint of the last interval we chose. That's a lot of words, so let's see a picture. For example, let us say you have chosen this as I1 and this as I2. So now when you want to choose I3, you only need to consider the intervals which lie completely to the right of this endpoint, like this one, this one, this one, this one, and this one. These five intervals are the only ones you need to consider because of the way we are constructing S. Now we are putting in elements in an ordered fashion. So yeah, like if suppose you chose S so that you first put in this element in S, this was I1, then you would only need to consider these four. Like you won't need to consider these four, even though they don't intersect with this, because now T has a new restriction that you now the construction of S has a new restriction that you put in elements in an ordered fashion. So now T will be only these four elements and won't include these four elements. So yeah, I hope that was clear. So okay, so now how do we choose IM plus 1 so that suppose you have built the S set S up to IM, then how do you choose IM plus 1 so that the size of T is reduced as little as possible? Then we have the following heuristic, like choose Im plus 1 to be the interval x in T such that Rx is smallest. That is, the right endpoint is smallest. Basically, the interval Im plus 1 lies as much to the left as possible. Again, I'll show you an example. So suppose you chose this interval, and this is your current S set S. Then the next interval you choose will be this one, because this is the interval in T. T consists of this. It consists of these seven intervals. So this is the interval with the leftmost right endpoint. So we choose this. because then after that you can sort of imagine an imaginary line. So first the imaginary line was like here at the right endpoint of this interval. Once you choose the next interval, it will move to the right endpoint of that interval. So if we choose this interval, the imaginary line is here, and we can next choose any intervals that lie completely to the right of that line. But if I first chose this and then chose this, then the imaginary line would go directly here. So the size of t would be reduced more if we choose this than if we chose this. So our heuristic is choose im plus 1 to be the interval x and t such that rx is smallest. And we can check that this works for all the examples we've considered so far. Like just check this example. Firstly, we'll choose this interval because it has the leftmost right endpoint. Then we would choose this one because same reason. And then again this one because again t is 1, 2, 3, 4, 5, and this has the leftmost right endpoint. And then finally you choose this one to get this optimal selection. So we can, and you can check that it works for the previous two examples also. So this one works for all the examples we've considered so far. And it turns out that this is the optimal solution. Like if you try enough examples and try to come up with counter examples, you won't be able to come up with counter examples because it is the correct algorithm. So now we try to prove that this algorithm should always give you the optimal solution. So what we do is we now try to prove that this strategy actually works by trying to reduce any optimal choice of intervals to a greedy choice. What I mean by an optimal choice of intervals is any choice or any valid selection of intervals which maximizes k. And what happens in this problem is the greedy choice. Like the greedy choice is fixed. Like there is only one greedy choice that you can make, like 1, 2, 3, 4. This is the only greedy choice. Like the greedy choice is fixed. There's only one greedy choice. But in many cases, it can happen that there are more than one solutions which maximize k. Like there are selections which maximize k are valid but aren't the greedy choice. So what we'll try to do is like we'll pick up any optimal choice of intervals and change it step by step into a greedy choice. So it is explained better here. So suppose the set U containing I1 less than I2 less than Ik is an optimal choice of interval. We will change the subset of intervals to the set U containing G1 less than G2 less than Gk, which will be chosen according to a greedy strategy. So this will be our greedy choice. So what we'll do is at each step, what we'll do is we'll replace ij by jj1 gj by one, going from j equals 1 to j equals k, and claiming that u remains valid at each step. So what we'll do is first we'll change I1 to G1. So the set u will become G1 less than I2 less than Ik. Next, what we'll do is, and we claim that once you have made the set G1 less than I2 less than Ik, it is still a valid selection, like no two intervals intersect in it. Next, you'll do is you will change I2 to G2. So your selection will become G1 less than G2 less than I3 less than Ik, and we'll claim that the selection still remains valid. That is G1 less than G2 less than I3 less than I4 less than Ik is also valid. So we keep in replacing the ij's by gj's one by one until we have replaced Ik by Gk, at which point the set U has become G1 less than G2 less than Gk, and it is still valid, and it has the same size as the original selection. So it is an optimal solution, which is our greedy solution. And we'll prove all this using induction on J. So now suppose so we'll be working with this example for proving this for the illustration part for images. So yeah, here you can see that this, the green part, 1, 2, 3, 4, this is the greedy choice which optimizes, which is an optimal solution. But there exists an optimal solution which isn't a greedy solution, like these blue intervals. These form an optimal solution, but they aren't a greedy solution. And these gray bars are just random intervals that didn't get chosen, that one part of this optimal solution. and aren't part of the greedy choice also. They are just randomly there. So what we do is, first we have I1 less than I2 less than I3 less than I4. Well, what we do first is we replace I1 by G1. Yeah, so initially what we think is if S equals phi, then T is this whole set of intervals, and we can make a choice for G1, and G1 will be the interval with the leftmost right endpoint. Like, this is the first right endpoint. No right endpoint lies to the left of it. So what we'll have is ki R G1 is less equal to R I1. That is, this right endpoint lies to the left of this right endpoint. So if we take this G1, this I2, this I3, this I4, then they won't intersect because this lies strictly to the right of this, strictly to the left of this. So G1, I2, I3, I4 will form a valid choice. So for our induction, the base step is done. You can change I1 to G1. So now suppose U has become G1 less than G2 till less than Gj less than Ij plus 1 till less than Ik. So then we consider what happens in a selection if you had taken S equals G1 G2 Gj. Like, suppose for this I'll be illustrating this for j equals 2. So suppose you have built up G1 G2 and you still have I3 I4 remaining. So the light green ones and the light blue ones are the ones which are currently forming U. So yeah, if S was G1 and G2, then T would contain Ij plus 1, like G1 and Ij plus 1, that is I3. So T would contain I3 because G1, G2, I3, I4 is a valid selection. So I3, and it is ordered like G1 is less than, G2 is less than, I3 is less than I4. So I4 will form part of T if S equals G1 and G2. So the set T is not empty at this moment. This is important. So please pay attention. So what this says is that since I3 is a part of T currently, T is not empty. So we can make a choice from T. And what choice we make is we again choose Gj plus 1. That is the smallest, that is the interval with the leftmost right endpoint, and it will come to be G3 because the previous two intervals are G1 and G2. So this is the same choice you would have made for the greedy algorithm. Now you choose. So this is the same choice you would have made in that case. So this interval that will be chosen will be G3, and again it will lie. Its rightmost endpoint be less will be less than or equal to the rightmost endpoint of I3. That is Rgj plus 1 is less than equal to Rij plus 1 due to the definition of Gj plus 1. Gj plus 1 by definition is the interval with the leftmost right endpoint. So yeah, if you have already built up the set U up to Gj, you can replace Ij plus 1 with Gj plus 1. So you keep doing this until you've replaced all the elements of U and made it into G1, G2, Gk. So this proves that our algorithm works, that the greedy algorithm works. Yeah. So now we look back on all that we learned from this solution. So the underlying mega heuristic was reduce the size of T as little as possible, because that makes complete sense. Like, you are reducing the size of T at each step, and the size of S is increasing by 1 at each step. And to maximize the size of S, you need to maximize the number of steps. So to maximize the number of steps, you need to reduce the size of T as little as possible. So then what wrong in heuristic 2? It was also reducing the size of T as little as possible. What we need to realize is that we are only optimizing this thing locally. Like, what we were doing in heuristic 2 was, suppose currently the size of set T is 5. So what you're doing is you're looking for the largest size of T to which you can reduce. So suppose the currently the size of T was 5, and in the next step it is possible for you to reduce it to size 4. But then it might happen that if you reduce T to size 4, then in the next step the only choice for you is to reduce the size of t to 0. Like once you go from 5 to 4, it might happen that the only choice available for size 4 is to go directly to 0. However, like it could have been possible for you to reduce the size of say set t from 5 to 3, and then go from 3 to 2, and then go from 2 to 1. So locally, it seemed like reducing the size of t from 5 to 3 is worse than reducing the size of t from 5 to 4. But then once you go to 4, you have to directly go to 0. But if once you go to 3, you can go to 2, then go to 1, then go to 0. So yeah, since we were only optimizing it locally, how exactly we do the optimization makes the difference between failure and success for heuristics 2 and 3. And if we think deeply about it, we see that the main difference that matters is in heuristic 3. Suppose on choosing interval A, T will become TA, and on choosing interval B, T will become TB. Then either TA is a subset of TB or TB is a subset of TA. Like, for example, suppose you have chosen just this, suppose you have chosen, yeah, the first two intervals, I1 and I2, and then in the next step, suppose you choose this is A. If you choose A, then T is this interval and this interval. It contains these two intervals. If you choose B, suppose this is B. If you choose B, then T is just this interval. So TB, which is this, is a subset of TA, which is this element plus this element. And this is valid for any two choices of intervals you can make at any stage. So what we have is like if you choose TA, then any choice that you could have made after choosing B, you can also make after choosing A, because TB is a subset of TA. So like you didn't lose any choice. So in that way, this structure is much stronger. However, if we followed heuristic 2, we would have only considered the sizes of TA and TB. Like whichever set has the largest size, we choose that, and that doesn't necessarily have to work as I explained before. Okay, so now we are done with this. So yeah, so proving that a greedy algorithm works is really important, because a really solid seeming heuristic can end up crashing and burning for some case, and that just leads to frustration and loss of points. Like you might not even realize that you the wrong answer verdict you're getting, is it because of wrong implementation or because of an underlying issue with your algorithm. So if you don't prove your greedy algorithm, then these issues can happen. So yeah, it is better if you prove your greedy algorithm. And it is important to come up with counter examples. And one way to do it is by challenging the underlying assumptions of your heuristic and constructing test sets accordingly. For example, if we go back to heuristic 1, our underlying assumption was choosing smaller intervals makes sense because smaller intervals have less number of intersections. But if we try to challenge that assumption, we can come up with this example where small intervals have a large number of intersections. And okay, so for heuristic 2, it is kind of hard to come up with the counterexample. I don't really know how to motivate that. But the underlying logic in some way is just to challenge the assumption that this is the best way to locally reduce the size of t as little as possible. Then you need to play around with a lot of examples to be able to come up with the counterexample. So yeah, this is like a hard counterexample to come up with. Yeah, so yeah, we are done with that. So now I'll just quickly mention some proof strategies we have for greedy algorithms. One of the proof strategies is just to consider the optimal solution and try to reduce it to the greedy solution. For example, especially when non-greedy optimal solutions also exist, like for this problem, non-greedy optimal solutions also existed. So what we did was we simply reduced this solution to this greedy solution. We slowly changed this solution and made it into a greedy solution. So yeah, this is especially nice when non-greedy optimal solutions are also there. And another strategy is direct comparison with the optimal solution. This can also be helpful when the only optimal solution is the greedy solution. Like no optimal solution exists which doesn't follow a greedy strategy. So what you can do is you compare an optimal solution A with the greedy solution G, and prove that if A is different from G, then you can make a local change to A. Like you can make a small change to A in some manner so that it is strictly optimized. And how do you decide this? What small change to make? That change is decided based on how A and G are different. So you make some small change and you end up strictly optimizing A further, which is a contradiction because you already chose A to be an optimal solution. So yeah, this is another way to prove that greedy algorithms work. And inequalities and monovariants related to the quantity we are trying to optimize are often helpful. Like in the previous problem, if we go back to this definition, yeah, the size of S is a monovariant, and in each step. So what do I mean by monovariant is a monovariant is a quantity that either only decreases or only increases. Like it can't increase and then decrease. So it varies in one direction. Mono stands for one. Yeah, so the size of S is a monovariant. It only increases and it increases by one at each step. And the size of T only decreases and it just keeps decreasing until you hit zero. And we also utilize inequalities. If you look at it, like this is basically the idea of inequalities. So yeah, we can see inequalities and monovariants more prominently also. Like here, inequalities and monovariants were a part of the solution. Sometimes they can be the main heart and soul of the solution also. So, and induction and contradiction are of course basic proofs of basic methods of mathematical proof. So of course they are seen quite a lot. So now I'll just quickly consider another example before we start discussing contest examples, like problems from actual contests. So in this example, what we have is we are given n real numbers a1 less than equal to a2 less than equal to n. So the array is sorted. You have to find x so that fx equals sigma sum from I equals 1 to n mod x minus ai. So basically you have to minimize the sum of the distances of x from the elements of the array. So for this problem, the idea of making small local changes is very helpful. And in a way you kind of look at the derivative of fx. Like in fact in this problem you can actually work with actual derivatives because it is like a normal function. So yeah, specifically what we'll consider is what happens to fx when we change x to x plus epsilon for a small epsilon greater than 0. So we again have some notation. So let Sx denote the number of ai satisfying ai less equal to x. S stands for small. So yeah, Sx is the number of ai which are less equal to x, and Lx is the number of ai satisfying ai greater than x. L stands for large. Then note that on changing x from x to x plus epsilon for a small epsilon greater than 0, when you do that, fx will change by sx minus lx times epsilon. For example, suppose initially x was 6 here, like 1, 3, 8, 9, 10 is our array, and x was 6 here. So you increased x by epsilon equals 1. So you made x equal 7. Then its distance from all the elements that were smaller than it increases by 1. So here the contribution is plus 2. But its distance from all the elements that were larger than it decreases. So here the contribution is minus 3, minus 1 from each of these three elements. So the total change is Sx minus Lx into epsilon, like S was 2 and L was 3. And how big can epsilon be? What exactly do I mean by small epsilon? Epsilon should be small enough so that x doesn't end up exceeding any element that was initially larger than it. Like we can have till epsilon equals 2, but if we choose epsilon equals 3, then x will become 9 and it will end up exceeding 8. So we don't want that. So epsilon should just be small enough so that it doesn't end up exceeding any element which was initially larger than it. So now what we have is that s minus L of minus infinity is minus n. Basically, when x is all the way to the right here, then all the elements of the area are larger than it. So s minus L is minus n. Like in this example, it is minus 5 when x is here. and s minus L of infinity is equal to n. Like when s is all the way to the right, then all the elements are smaller than it. So s minus L of x is n, which is equal to 5 here. And s minus L is a non-decreasing integer function. Like its value is always an integer, and it is non-decreasing because when you move x to the right, the number of elements to which are larger than it can only decrease, and the number of elements that are smaller than it can only increase. So x must lie just beyond the region where s minus L of x is less than 0. Like if here s minus L of x was 2 minus 3, which is minus 1, so this is not the optimal choice. You increase it, you get to x equals 7. S minus L of x is still negative. You increase it, and then when you get to here, s minus L of x becomes plus 1. So yeah, when x equals 8, s minus L of x becomes plus 1 because these green elements 3 are less equal to x and these two are greater than x. So s minus L of x becomes plus 1. So you don't need to increase x further. So x must lie just beyond the region where s minus L of x is less than 0. And you can see that x will be the median of the sequence. Like if x equals, yeah, that is x equals n plus a n plus 1 by 2, if n is odd, and x will belong to the interval an minus 2 comma an by 2 plus 1 if n is even. Like x will be able to take any value in this interval for n even, and for odd it will have this single fixed value. For example, here n equals 5 and x equals a 5 plus 1 by 2, that is a3. So basically, if you want to intuitively understand it, you can just say that x must have as many values in front of it as there are behind it. Like this is not a very precise statement to make, but it intuitively makes sense. So yeah, that's it for my part right now. So now I guess Adil will discuss a problem from greedy algorithms followed by area.
Hello everyone. So I'll be discussing this problem. It's visible, right? The screen is visible. Okay. So in this problem, we're asked that given a string of length n, which consists of only t or m characters, if it's possible to partition it into some disjoint subsequence such that all the subsequence is equal to tmt, and also that the n given will always be divisible by 3. So let us see some examples. So all these subsequences should be TMT. That is the total number of m. So if the m is sub n is equal to 3k for some integer k, then in this string there should be a total number of 2kt and 1k. That is for every m there should be 2t. But this does not satisfy the whole condition of the program of the question. Suppose in this example, uh, there are two t but only one m, but this is not valid as there is no t before this m. So this will give wrong answer. Now in this, suppose for this example, uh, for this m, there is a t before it and there is a t after it. Uh, Now let us choose some method for optimally finding the solution. So suppose we first take the first t in the string and give it to this m or before, and the next occurrence in the next occurrence of t after this m as after this. So this, and this. These three elements are used. Now for this m, there is no t before it. So this approach is not correct. We shall try another approach. Now let us try to give the first occurrence of the t in to give to the first m as before, and the last occurrence of the t in this string to this m for after. Now this, and this, these three are used. Now for the second m, we'll use the this occurrence of t. It is the second occurrence from the starting. Give it as before, and the second last occurrence of the t in the string to give it for after. This is valid. But if we now see this example, for this m, we'll give the first occurrence of t for before and the last occurrence of t for after. Now these three are used. But for this m, we'll use a second occurrence of t as before. But the second last occurrence of the t is before this m, not after. So this approach is also not correct. Now let us see another approach. Now for this m, we'll use this t, the first occurrence of the t as before, and the t that is after the 2, that after the k number of t has occurred, that is the number of m is also k and the number of t before should be m. After the k occurrences of t has occurred, the next t that will occur will give this m for after, that is this. So these three are used. For this m, we'll use a second occurrence of t and this then after k has occurred, then from there this first t, second t, this t as after for this m. Now these three are also used, so this is valid. Now we'll check the same thing in this example. For this m, we'll use this t as before, and after k 1 2, after k occurrences of t, the first occurrence of t, it is this one. For this m as after. So now these three are used. Now for this m, we'll use the second occurrence of t, and then after t has after k number of t has occurred, from there the second 1 2. This is also valid. So suppose we take two arrays in which we store the indices of the t and m, that is t 0 2 4 5 and m 1 and 3. So for the first m, the first index m, we'll use the first occurrence of t and the element of t, that is 1 plus k, that is the 1 plus 2. Third element, third index of the t, that is 4. And we can see 0 is less than 1 and 4 is greater than 1. For this three, the second is 2 and then 2 plus 2, that is the fourth occurrence of t, that is in the fifth indices. You can see second 2 is less than 3 and 3 is less than 5. So it's also correct. For every mi, there will be ti plus k greater and ti less than mi for 1 I k. Let's try to code this now. Also, the constraints in the t in the question given for t is 1 to 5000 and for n is 3 to 10 to the 5. That is, we can store it in int data type. No need to use long int. So now let's try to code it. Int t. Now we'll declare two arrays to store the indices of t and m. Using a vector array. to store indexes of t in string. This is to store indexes of m in string. Now after storing, we will check if the size of this t array is equal to 2k. So first, let us take k equal to n by t. If t dot size is equal to 2 into k and we'll check that. Or m dot size is not equal to k, means this simply output no. Else we'll check the condition, this condition that for a ti is less than mi and mi is less than ti plus k. Let us take some flag. If t checking if this does not happen, so we'll just put a not. So if this at any point of time this does not satisfy the condition, then we will change the flag equal to 1 in break. We will check flag is equal to 0 and output yes, else output no. And after just go to next line. Now let's run this program. Uh, it's giving us the correct solution answer here. Yes, no, yes, no. Now let's try to submit this. Also, the solution is of the time complexity or O of n. It's accepted. Now we'll go back to Sawmill.
Am I audible? Okay. So I would be presenting the solution of a greedy task today. And one thing that we should remember while solving a greedy task is that unlike other topics that you have studied up until now, greedy does not require you to have any very specific knowledge. So you just have to try to experiment and take your intuition into account, and on the basis of that you can read the problem, think what would you do in it, then try it out, and this is how we'll go about it. So I chose this problem since it is based on bit operators that we covered last time as well. So the problem reads, you are given a collection of n non-negative integers a1 up till an. You are allowed to perform the following operation. Choose two distinct indices. If before the operation ai is equal to x and aj is equal to y, then after the operation ai is equal to x and y and aj is equal to x or y. And this operation may be performed any number of times. So basically we are given an array of numbers. We can choose any two distinct numbers, replace one of them by the and of the two numbers and the other one with the or of the two numbers. After all operations are done, compute sigma ai square. So once you're done with all our operations, we have to compute the sum of the squares of all new elements in our array. What is the largest sum of squares that you can achieve? We have to work under the given constraints of n less than equal to 2 into 10 to the power 5 and ai less than 2 to the power 20. So this is another hint of using something related to bits, since we are given 2 to the power 20. So that means we have 20 bits. So yeah, these were the sample cases given to us. In the first case, we had one number in an array, which is 123. So here there is no optimization or no operation that we can perform. So our final answer would be the square of 123, which is 15129. In the second example, we are given an array with three numbers, 1, 3, and 5. Since we are dealing with the binary representation, I've written it in the binary form as well. So if I initially calculate the sum of the squares of all the numbers, that comes out to be 35. Now we are allowed to perform the operation as many times as we want to. Let us assume we first carry out the operation between 1 and 3. So if you carry out the operation, we get 1 and 1, 1 is 1 and 1 or 1, 1 is 1, 1. So essentially 1 and 3 is 1 and 1 or 3 is 3. So doing this operation does not bring out any change. Similarly, if we take 1 and 5, so we get 1. And if I take 1 or 5, I get 5. So this operation also does not result in any change. However, if I take 3 and 5 and I take 3 or 5, I get two different numbers from what we had initially. So 3 and 5 gives us 1 and 3 or 5 gives us 7. So after this operation is carried out, what numbers do we have? 1, 1 and 7. So in this case, the sum of the squares of all numbers present in the array now is 51. We cannot further carry out any useful operations because 1 and 1, 1 or 1, 1 and 7, 1 or 7, these essentially would result in the same numbers that we had initially. So our best possible answer for this case would be 51. So now we'll start to think about how to proceed about the question. The first observation that we make is that the bits having different significance are mutually independent. So if I have some ai and aj and these are the corresponding bits with equal significance, then what happens to the red bits does not affect the blue bits and does not affect the green bits. So this is one insight that we can use during our solution to the question. Now this helps us reduce the problem into individual bits, which can be 1 or 0. So we have 4 different cases that ai gives us 1, aj gives us 1, ai1, aj0, ai0, aj1, and ai1, aj1. So 1 and 1 is 1, 1 or 1 is 1, 1 and 0 is 0, 0 and 0 is 0, and 0 or 0 is 0. And if both are different, 1 and 0 is 0, 1 or 0 is 1. These are the only possible cases that we have, and on the basis of the results of these computations, we can find out that the number of on bits or the number of ones occurring at a given position or a given significance remains constant. So what this means is that whenever we carry out any operation, the number of bits would remain the same, but a bit can be shifted from one number to another. So if we have, say, 1 here and 0 here, and we take the AND operation, so we might result with a 0 here and a 1 here. This is the only possible change that we can bring about by doing the allowed operations. So now the question comes that how many operations should we do so that's to optimize our solution. So without loss of generality, let us assume we take two numbers x and y, which belong to the array. So like x is ai and y is aj. And let us assume x greater than equal to xy. So after the operation, since the number of on bits is not changing, one number would get increased and the other one would get decreased. So let us take, since x is greater than equal to y, so let x and y be y minus t, and x or y is equal to x plus t. So the sum of squares before the operation was x square plus y square, and after the operation is x plus d whole square plus y minus d whole square. So this comes out to be x square plus y square plus 2d square plus 2d x minus y. Given x greater than equal to y and d being a real number, this value is always greater than this value. This means that no operation would result in a decrease in the sum of squares and can possibly result in an increase in the sum of squares. So does that mean that we should do infinitely many operations so as to maximize our result? Doing infinitely many operations would obviously give us the best possible answer, but that would obviously not be feasible. And moreover, it is not even required, because we observe that when d is equal to 0, then doing these operations does not make any difference. Even in the initial case that we saw, here as we saw that doing an operation on 1 and 3 does not bring out any change. So similar is the case here. We should not do any operation such that d is equal to 0. Now we have to see which case gives us d is equal to 0 and which case gives us d not equal to 0. D is not 0 when our y, which is our smaller number, has a position where its one bit is on, but that particular bit is off in x. So after the operations, what happens is that one off bit gets shifted to the larger number, and the one that is made by the or of the two elements. So this gives us a positive d. However, if we have y off at all the bits where x is off, where x being the larger number, this means that the operation would result in d is equal to 0. And such a case in which y is off whenever x is x being off implies y is equal to off, and x is greater than equal to y, such a case is known as y being a submask of x. So we have to not consider these cases. So now we'll proceed with doing the mathematical part of the question. So we'll, now that we have the number of bits that are on for any given position, we will reassign these bits such that we can make maximum larger numbers, because we saw that given the nature of the function, maximizing a number would always help increase the sum of squares. For example, let us have initially an array of 6 numbers, the one written in this corner, and these being their binary representations. So we can calculate the number of on bits for any given position. So the number of on bits for this position would be 4, for this position would be 2, for this position would be 0, 1, and 3. So we get the number of on bits. Now we would reassign them such that the total number of on bits remains the same, but we can maximize the value of a single number. So we assign this bit as on to the first 3 numbers, this bit as on to the first number, this bit as on to the first 2 numbers, and so on. So this final array of numbers that we get is the one with the maximum possible value. So the sum of squares for this new array that we have constructed now would be the maximum. So now, once we have thought of a strategy, we can go on to writing the code. I wrote the code for the same. So we are given that the question has only one test case. We input the number of elements in the array. We input the array. Now we have another array by the name of CTR, which has the number of on bits for any given position. So initially, we would initialize the array to 0. Now we would go through the array and we would see that if that bit is on, then we would increment this counter for that particular bit. So for I equal to 0, I less than n, I plus plus, we get an AI element of the array. For j is equal to 0, j less than 20, j plus plus. So we see the jth bit of AI. If it is on, which is given by the AND operator, we would increment the counter for that value. Now, we have to reassign these bits. So for reassigning, first of all, we make all the elements 0. Now, what we do is that we take the counter and increment each value of AI up until we run out of more number of on bits for that given value. So we increased AI and decreased the counter, and we kept on going until the counter is equal to 0. This way we have traversed the array, and finally we sum up the values of the squares of all the values and output the answer. I submitted the solution and it got accepted. So I hope it is clear. If anyone has any doubts, you might ask.
Okay, hope I'm audible. So I'll be discussing a two pointers method, which is often used alongside with greedy algorithm to solve problems. So I'll just jump in with an example because the method is yeah, I'll jump in with an example as the method is generally rather vague and there's a lot of room for changes. So it'd be easier if we work with a concrete example first. So consider this problem. You have an array of n positive integers and you have to find any all intervals or subarrays whose sum is less than or equal to some number s, which is given to us in the input as well. Okay. So now, as an example, for making it clear, if we consider this array to be the array that's given to us and s to be 7, then 1, 1 plus 2, 1 plus 2 plus 4, all of these intervals have sum less than 7. And along with that, you can see similar intervals work, and you, as such, you get total of 11 possible subarrays. Now, and just as a piece of notation, I'll be using a square bracket and a normal parenthesis to indicate half open intervals. So 0, 2 refers to index 0 and everything up until but excluding index 2. So 0, 2 refers to these two numbers. Okay, so for and just as a piece of terminology to make working with stuff easier later, we'll call a subarray which has sum less than s small. So we'll make a rather simple observation at first. If a given subarray is small, and then any subinterval which lies inside it will also be small, because all the numbers are positive, and if you simply remove a number from the interval, its sum will be strictly less. And along with that, if some subarray is not small, and if you have a larger interval which contains it, then it will also not be small because you add some positive integer to it, and if its sum is already s, it will exceed s. Now, if and with just this operation, you can actually solve the with just this observation, you can actually just solve the problem from using binary search. We simply iterate through all possible values of L, and then you binary search to find the largest R. Because if you look at the condition, what it tells you is that you have you can keep on extending the array. You can keep on extending the current subarray until its sum is just less than S, and if you extend it any further, its sum will soon exceed S. So if you remember from our previous binary search lecture, it satisfies the property of being able to split it into red and green regions, and you simply binary search to find the position where the green region and red region meet. It's the same idea. So you binary search to find the largest R, then any subarray of this will be also be small, and you have to add all of these contributions to the answer. Along and any larger subarray can't be small, so you simply don't consider them. Now, while the solution works and will probably pass for any case, you can do better. You can drop the log n factor and simply have an ON solution. So in the last step, we only use the fact that you can extend the array to the right. However, we never use the fact that when you move the left endpoint of the array as well, it still satisfied the smallness condition. So two pointers will also make use of this fact, and that will allow us to reduce the time taken. So the idea is simple. You iterate through all L as done in the previous step. And earlier we found R independently each time for each L. This time you also keep track of R. And whenever you move from the current L to the next step, L plus 1, you know that R will have to increase because of the previous R will either increase or remain the same. So it will not decrease because again is just this observation that any subarray will be small. So you get this bound on your new R. And that simply, and if you keep track of it using two different pointers, the name of the method, you can get the solution. I'll do a sort of dry run to make it a bit clear. To start with L is equal to 0 and R is equal to 3, because 1 plus 2 plus 4 is 7, and if you add 2 to it, it exceeds 7. So this is your maximum interval. Now you move to the next step. We remove one's contribution, we try to extend it further, but we notice that if we subtract 1 and then we add 2, it again exceeds 7, so R remains unchanged. Now if we now again move to the next step for L, R, we can get rid of this 2 and we add this 2 and we can increment R. And again for 2 we and again for L is equal to 3, we get rid of the 4, we add the 5 and we get 7. And you can keep doing this repeatedly to get all of these LR values and just add R minus L to the answer for all of these. So looking at how you implement it would make understanding a lot easier, because two pointers is generally more of an implementation side thing after you make all of your operations. So you store a variable called answer to store the current answer. All right, cool. So you keep, and along with this, keep a variable sum, which will always store the value, we maintain the invariant that sum will contain sum of all the values which lie in the interval L to R. So, and again, like the previous step said, we try to, as we showed in the previous example, we keep trying to push the value of R further in each step. For doing this, we simply check if adding the next value makes it exceed S. If it doesn't, we move R forward and we add R minus L to the answer. And if you now, and when we move to the next L, we remove the contribution of AL. And so this entire algorithm works in OM, and it is and it gives the right answer because of all the observation, because of the simple observation we made earlier. Now we do a time complexity analysis of the solution because it isn't entirely obvious how all the L and R are moving. Because if you consider it, we have two while loops inside each other. We have two loops inside of each other, and generally that leads to an O(n) square solution. So here, when we look at L, we move it by one in each step, and this total sums up to n step. However, R may move arbitrarily times in each step. So, for example, here it was initially 0, then moved 3 steps. Here it did not move at all. Then it moved 1 step. Again, it moved 1 step. Then it remained the same, move 1 step, and so on. And you can even construct examples where in the first step it moves n steps and then it doesn't move again, or it moves half of the array in the first step, then again moves forward by n by 2 steps in the next array. But the thing is, we are moving R in only one direction. So it only ever increases. It never decreases. And along with this, R initially starts out with the value 0 and ends at some value less than n because of the condition we put on the while loop. So the total time taken due to R would necessarily be less than or equal to n. And if you simply add these two contributions up, this gives you an ON solution, which is faster than the previous ON log n solution that we came up with. So in general, this is like the very vague skeleton of a two pointers method solution. Again, all of this is very vague because in how many possible ways you can use two pointers. You keep track of two pointers and you usually move these pointers monotonically in some fashion. For example, in the previous case, we only moved R forward and L forward. In some cases, you move R backward, but you only move it at some maximum number of steps. And along with this, you keep some invariants in which, in this case, we maintain the invariant that sum is 0. That sum is that of L to R. And you stop the current iteration when once a condition has been achieved. You process that information you got from this iteration. For example, here we added R minus L, and then you move forward and you keep doing that. And the number of pointer moves, while they in each iteration might be unbounded, as we said that it might have n. One iteration might move n steps, but then in the later steps it might not move at all, which gives you a general bounded way of moving these pointers. I'll be going through some common variants in which this method is implemented. So all of these, other than the last one, all of these are just names I use, and these aren't standard at all. So but these might be very useful while implementing these algorithms. Generally, because two pointers is a method which, with all of the minute changes you can make, is very easy to mess up while implementing. And unlike with the example we saw with binary search in previous lectures, there's no one universal method that would work with everything. So, for example, with the case we worked with, you find the maximal interval which remains good. So for the problem we looked at, goodness was defined in terms of being small. having a small sum. And so you you iterate through all L, and you keep incrementing R, and you keep adding all the contributions, and then you process LR. While this is some vague good, can be some vague function. For our case, it was just checking that sum is less than S. In other cases, might be just checking it has enough number of elements, it has few elements, and it again can be, these add and good functions can be very, very general. And you can also implement it in another fashion where you fix the right endpoint and you keep moving the left endpoint forward. In the previous case, we had fixed the left endpoint, then we adequately move the right endpoint forward. We might instead fix R and move the left endpoint forward. Another variant would be like disjoint interval splitting. So an example would be you have an array of integers. You want to split it into different subarrays such that each subarray is non-decreasing. So for example, in this case, you'd split this array into 1, 2, 3, 2, 2, and 1, because each of these individual subarrays are non-decreasing. Are non-decreasing. So how you do that is again maintain two pointers L and R. So you'd maintain two pointers LR. You'd initialize R to be L plus 1, and while the two adjacent values are satisfy the non-decreasing condition, you keep extending R, and you get an interval LR. And then you skip L forward to the previous value of R. So for example, you might take L and R to be 0, 0 here. Then you keep moving R forward, and you get and you get R is equal to 3. Then you move L, you jump L forward to the current position of the current position of R. Then you keep again find this maximal interval, and you keep hopping in that manner. And the generic code would look something like keep 2 pointers LR. You reset it at your new interval that you're working with. You add the contribution of one of the points, and then you again keep expanding it while the interval still remains good. And again, good is some generic, very generic condition. And another would be like a forward backward iteration in which you maintain 2 pointers L and R, and you move, and L moves forward while R moves backward. And all these movements need not have a very specific pattern. So it's not necessary that in each iteration, if you would only move by one, it might move by a lot of steps. So for example, if you take the problem 2-sum, and you have a sorted array of integers, and you'd like to find any two integers with sum to x. So what you can do is consider 2 pointers L and R, which are point to the minimum and the maximum element. What you notice is that if you move the left pointer forward, the current sum of these two values will increase because A is sorted. So when you move to the next possible L, the sum will have to increase as this AL plus 1 is larger than AL. And similarly, when you move the right pointer backward, the sum will decrease because AR minus 1 is less than AR. And you keep doing that. So you start with the left and right endpoints. If the sum is less than x, you move the left pointer forward because that increases the sum. And if the sum is greater than x, you move the right pointer backward because it decreases the sum. And our target value is x. So we keep doing this repeatedly, and if at some point the value equals x, you break away, and that you found your answer. This can again be made more general with by replacing these two conditions with some generic condition 1 and generic condition 2. So yeah, this is generally how you work with 2 pointers. In case you have any specific question, you can just put them in the chat. And now after this, I think Chinmay will be doing an example of a 2 pointer question.
Am I audible? Hello. Okay. So the problem which we'll be discussing today again is an application of the two pointers approach that Rishabh just discussed. It is, to be specific, it involves forward backward iteration as he named it. So it's I would say not an easy problem, but two pointers makes it pretty. I would say solves it pretty efficiently. So the problem is from lead code and it is container with most water. So the problem states that you have an array, so basically n non-negative integers a1 a2 up till an, and each represents a coordinate I comma ai. So basically this will be 1 a1 2 a2 up till an, and they will hence represent n vertical lines such that the two endpoints are at I and I0 and AI and I0. So for just to give you an example of what the description means is that, for example, in this case, we have this array 1, 8, 6, 2, 7, 1, 1, 8, 6, 2, 5, 4, 8, 3, 7. So the first pillar is of height 1 and is at x is equal to 1. The second pillar is of height 8 and is at x is equal to 8. The third pillar is at height 6 and so on. So this is an array. The array is one index, which is contrary to how they are generally indexed in programming languages. So they are one index and they have negligible thickness, but their height is represented by the value at that index. So for they define something to be how much water does a container contain. So for two lines, two of these pillars, we have to find which of these two lines contain the most water. So the idea is that you pick two lines. So for example, here they have picked these two red lines, and they try, and you can, when you pick two lines, you just disregard all other pillars. And if you consider these two pillars, this is the amount of water that will be stored. So it is somewhat proportional to the distance between the two pillars multiplied by the height of the smaller pillar. So they have given that we can't, you may not slant the container. So that basically means that we'll have to restrict the height of the water level till the smaller pillar, or if they're equal, till that height. So we have to find the pair which gives the maximum answer. So for example, in this case, if we choose these two red pillars, they itself give the maximum answer. And since the height is 7 and the distance between these two pillars is also 7, so the output is 49 for this test case. So I'll try to explain how we can use two pointers to solve this. So I hope there's no doubt till now in the problem, in what the problem is. So we'll move to the approach. So the idea is that two pointer basically in some sense is an optimization to the brute force approach, and in this case it is easy to see that brute force is like pretty intuitive. So we can just check all pairs and see which gives the best answer. So we can iterate over let's say I and j, and I and j for all ij which can, as a pair, and just check that does this give a better answer. So we can maintain a max answer variable, and we can just update that max answer after we check each pair. So since there are nc2 pairs, so that means that our solution is order nc2, or in other words n square. So it is not an optimal solution, but it does the work. And the idea is that we can use two pointers somehow to reduce the work it is doing. So here we are checking for each ij, and that leads to too many comparisons or checkings, and because of that we are the order of the solution becomes bad, and the solution becomes slow. The idea is that can we use two pointers to somehow like avoid unnecessary computations, right? So can we use two pointers, and can we observe something in the problem so that we don't need to do unnecessary comparisons. So before we discuss how two pointer will work here, I think the straightforward observation is that if I choose I and j and I want to find the the water contained as they define it in the question, corresponding to those two pillars, that will be minimum of height I and height j times j minus I. So for example, if I take this example, the test case, so for example, if I choose 1 and 2, so for example here, if I choose 1 and 8, the water that they can contain is this, right? So the water, or you can say the front area of that water column will be constrained 1 by the minimum height, so it will be 1 in this case, because this the index, like this is index 1 and this is index 2. So the first pillar is of height 1 and the second pillar is of height 8. So the water that can fill here will be proportional to the smaller height times the distance between the two pillars. So distance between the two pillars is what we get by j minus I, and the height is constrained by the smaller pillar, and that will be minimum of height I times height j. I think I by mistake wrote maximum, so yeah, but it will be minimum. So height I comma height j. So if we use the brute force approach, we'll have to check all pairs, and that will not be an optimal solution, because again, as I said, we'll be checking too many things. So can we do something which is better? So idea is that, if let's say I have this solution space, so this is initially 1 and this is n. So for some 2 pointers or some 2 pillars, I'll get the optimal solution. That is, for some 2 pillars, I don't know what and I don't know how now I'll find them. But for some pillars L and R, the solution will be optimal, right? So L can start from here and R can start from here, and we'll try to adjust them or move them in some in some particular manner, and at some point L and R will be optimal. That is, for this L and R, the water content is maximum for out of all possible pairs. So this like for thinking 2 pointers here is intuitive, because in some sense the answer depends on 2 positions, and we can maintain those positions using 2 pointers. And the way we move the pointers is efficient, so that we are avoiding extra computations. So what is the idea? The thing is that, let's say I have this example where I had this pillar 1 and this pillar, let's say 7. So the rightmost pillar is 7 of height 7 and the leftmost pillar is of height 1. I start my 2 pointers from here. So L is equal to initially at 0 or 1, depending on how you implement it, and R in this case, let's say, is n minus 1, since I'm starting from 0. So I'm trying to find which gives me the best answer. I'll globally maintain a variable which stores the max answer, which which will be the final answer, but initially it will be 0. Initially I've not found any answer, but I'm trying to find which 2 pointers gives the best answer, and I'll try to move them efficiently. So let's say this is the case. So whichever is a smaller pillar, in this case it is the left pillar, you can see that the water contained will be this. Now, in the brute force approach, for the smaller pillar, we were checking all possible right pairs. So we were going to 1, 2, 3, up till n minus 1, and doing that check again and again. But the observation is that, let's say, there'll be 2 possible pillars to the right of this left pillar. Either the pillar will be of a greater height, or let's say of smaller height, or even equal height. You can take them to be 2 cases or 3 cases. In any case, the water that can come here will at max be of height the smaller pillar, because if the pillar, this blue pillar, is greater, still we can see that the water is cannot overflow, so it will still be less than the smaller pillar and the height. And even if it is less, it will be further less. So if the right pillar is smaller, it will be further smaller, right? So the thing is that I have 2 pillars at 1 and 7, and for any other pillar 1 and some r which is not equal to n minus 1, I'm trying to see, does it give a better answer? So if I take this other pair, which I'm trying to see, do I even need to check these pairs? So the thing is, the width will increase, and this is strict decrease, it will always decrease. The height of the water column can never increase because it is bound by this smaller height. So the height will either be less or it might be equal to. So in the totality, the area that we are getting, or the water content which we are getting, will always decrease, because height is decreasing and width is decreasing, and height at most remains same, and it can also decrease. So the idea is that for this L and R pointer, if I get some answer, which in this case will be 1 into the distance between these two, let's say 8 or 7, whatever it might be, for all other right pointers, I don't need to check with this left pointer, because any other answer which I'll get with this left pointer will be worse. So the idea is, instead of in brute force, we are checking for all L, for this L, we were checking for all R. If this left pointer has a pillar which is smaller in height than the current right pointer, then I don't need to check for all other right pointers, because any answer which I'll get will be worse only. So it is in some sense a greedy approach also, and in some sense an optimization by efficiently moving the pointers also. So what I can do is, in this case, I can just move my left pointer by one to the right. So the right pointer moves to the left and the left pointer moves to the right. And now my solution space decreases, which means that now I have to find answers in which the left and right pointers lies in this interval. So I don't need to check for this, because I've already accounted for the maximum possible answer that this L pointer could have given with the particular right pointer. So I've already updated my max answer, but for any other right pointer, it won't give me a better answer. So I don't need to check. So what I'll do is I'll move the left pointer. And this can happen both ways. For example, if right pointer had a pillar which was of smaller height, for example, in this case, right pointer has a pillar of smaller height, any other left pointer to the left of the right pillar will give me a worse answer, or an answer that I've already accounted for. For example, here, let's say this was 7. So now let's say this becomes 8, and this was 7, and the previous pillar was 1. For 7, I've already accounted for all maximum possible answers to the pointers which I've already visited. So the left pointer is currently here and the right pointer is currently here. For 8, I have seen that since 7 is less than 8, all other left pointers here will give a worse answer. So I can just use 7 with 8 and see that does it update my max answer. If it does, I'll do that. Otherwise, I don't need to check for any other variable, since I will always get a worse answer. So in some sense, I'm trying to contract the possible solution space or the pairs which I have to check, and I'm updating a maximum answer. So it is a greedy approach, because I'll not check every possibility. I'm trying to use a global optimum here. So 7 and 8, it will form a global optimum for this solution space for 7. So I don't need to check again for 7. I can just update my maximum answer. So I'll keep moving my left pointers and right pointers until they come at the same place. So when they come at the same place, that means that there is only one pillar, and that you cannot form a container, or you can say the answer will be 0. So I'll keep doing that till my left pointers and right pointers coincide. Another thing is that this is efficient also, because my left pointer started from here and my right pointer started from here. So I'll never ever exceed I will never traverse more than the length of the array. So they'll meet somewhere here, which might be anywhere, but they'll never in totality traverse more than the length of the array, which is order n. So the pairs L and R which I'm checking are only n at max. So I'm optimizing from n squared to n by using this approach. So I hope the explanation is clear. So I'll just go through the code, which is pretty small. In lead code, actually, the way they ask the code is that they have this function which they expect you to complete. So and what they do is that they have this class inside which they have this public function which they want you to complete. So basically, you don't have to worry about input and output. So what you do is you just complete this function. They have the return type mentioned to you, and they have this input type mentioned to you, and you can just complete this function. And the way they run it probably is by creating an object of that class. So for example, they might create something of this sort, solution solve, and for that object they themselves figure or handle taking inputs and then call that function passing that input. So you all have to worry about this function itself. So I'll just go through the solution in case this would not have been a problem on lead code. So you have int 10 c and n, and since n is pretty small in this problem, 10 power 5, so you can just create a vector, and I'm just initializing this vector with n, which means that it will create a vector of size n, and then I can input elements. If I would haven't have done this, then what would happen is that this would give an error, because I'm trying to access some element of a vector which is itself not yet initialized. So this vector is a zero length vector, and I'm trying to like access elements which have not yet been initialized. So it's better to, since you know the value of the size of the vector, you can just initialize it so that you don't have to first input an element and then use pushback. So just saves time. And then I have made this object of the class solution, and I've called the function which I have to complete, and I've passed the vector to it. In this solution, I have this vector int height, which I'm calling by reference. So in case of vectors, you might have studied in the last lecture that vectors are although arrays, but you have to explicitly pass them by a reference. So if you remove this ampersand, then this would be a call by value, a call to this function, and the vector itself will get copied. Although it is an array, it will get copied. So we'll use this to which saves time and saves memory. So this function has a return type int, because the answer is pretty small. Because the length of the array is 10 power 5 and the elements themselves are of the range 10 power 4. So at max, the answer will be 10 power 9. So which fits into int. So I've initialized two pointers, which could have been L or R as in my solution, but here I've mentioned them to be I and J, and I is at 0. So since I've used C++, so everything is zero index. So I'm just shifting everything one to the left. So instead of one, I'm using zero, and instead of height dot size, I'm using height dot size minus one. And this is the answer which I'll return in the end. And I'm just checking for each pointer, I'm checking whether this answer needs to be updated or not. And I'm trying to avoid irrelevant or redundant comparisons or checkings. So I'm this loop is basically simulating the movement of the pointers. So I'm moving the pointers till they don't coincide. So while I is not equal to j, I'll move the pointers. So the for these current values of I and j, I'll check what the answer these pointers can give, and that will be, as we discussed, minimum height ij times j minus I. So height is constrained by the smaller pillar, and width is the difference between the indices of the pillars, which represents the width. So this can be a possible answer. Now, if height I is less than height j, for all j to the right of I don't need to check, as we discussed. So I'll just move I plus plus, because for this I don't have any use, because this will never give me a better answer. On the other hand, if height j was smaller than height I, do j minus minus, because for all left indices, this particular right index cannot give me a better answer. So I don't need to check for it, and I'll avoid redundant comparisons. And at the end, this while loop will end when both of them coincide, and I'll return my answer. So it works. For example, here we have 9 samples, and this was a test case. So I can just run the solution. You can see that we get 49, and you can submit it also. It works. So I hope there were no doubts in the solution. So Somil will take over from here.
Yeah, hi. So I'll quickly discuss what ad hoc problems are and two strategies on how to solve them. Yeah, so I hope my screen is visible and I'm audible. Could someone please confirm that I'm audible? Yeah, okay. So now we'll quickly look at some what ad hoc problems are and how to solve them. Yeah, so ad hoc problems are those whose algorithms don't fall into standard categories with well studied solutions. Like they won't fall into categories like, yeah, dynamic programming or segment trees. So they don't fall into well standard categories. Each ad hoc problem is different and no specific is to solve them. But of course, the above definition is kinda vague. I can just take the solution of a problem and call it a new general strategy, a new general technique. And we're even gonna contradict the above definition further by showing you two techniques to solve so called ad hoc problems. Ad hoc problems usually rely more on pure problem solving ability and less on the knowledge of data structures and algorithms. So, trying out cases, making observation, and good problem solving habits in general are key. So, yeah, firstly, I'll just discuss what the pigeonhole principle is. It is just an intriguing name given to the following obvious but very useful fact that if you have n plus 1 objects and n boxes to put them in, then some box will have to have greater than equal to 2 objects, which is obvious. And we also have the generalized pigeonhole principle that if you have n objects and k boxes to put them in, then some box will have greater than equal to ceiling of n by k objects, and some box will have greater than equal have less than equal to floor of n by k objects. By ceiling of n by k, I mean the smallest integer which is greater than equal to n by k, and floor of n by k is the largest integer which is less equal to n by k. So yeah, this is also obvious because if every box has less than ceiling of n by k objects, then the total number of objects will have to be less than n. And if every box has more than floor of n by k objects, then the total number of objects will have to be greater than n. So yeah, this is the generalized pigeonhole principle. So now first I'll show you the problem I'll be discussing. I'll be discussing the problem Eric Tacto. So Eric Tacto, it's a problem in code forces. Yeah, so Eric Tacto gave Monaghan the following challenge in order to intimidate him from taking his top contributor spot. So we have a tic-tac-toe grid with n rows and n columns. Each cell of the grid is either empty or contains a token. There are two types of tokens, X and O. If there exist three tokens of the same type consecutive in a row or a column, it is a winning configuration. Otherwise, it is a draw configuration. Like you have three X tokens in a consecutive row, consecutively in a row, so it's a winning configuration. Three consecutive O's, three consecutive X's, and three consecutive O's. And here you don't have three consecutive X's or three consecutive O's in a row or a column. So this is a draw configuration. Similarly, this is also a draw configuration. This is a draw and this is a draw. So in an operation, you can change an X to an O or an O to an X. Like you could say take this X and make it an O. You could take this O and make it an X. Let k denote the total number of tokens in the grid. So initially you are given the n cross n grid, and some cells of the grid will have tokens on them and some won't. Like here, these three cells have tokens on them and these six don't. So what you can do in an operation is you can change an x to okay, I've already explained that. So you can change an x to an o or an o to an x. So what k is the total number of tokens in the grid. Like here k equals 3. Your task is to make the grid a draw in Atmos floor of k by 3 rounding down operations. So you can use Atmos floor of k by 3 operations and you have to make a draw. So basically this is currently a winning configuration. What you can do is you can change the middle x to an o. Then you would have xox and the configuration will now be a draw configuration. So you have to make the grid a draw in Atmos k by 3 operations. You are not required to minimize the number of operations. Like if it is possible to do it in two operations and you use three operations, then you are not penalized for that. It's fine as long as you use at most floor of k by 3 operations. Okay, so now let's look at the constraints. You have a single integer t, which is the number of test cases. T is in 1 to 100, and the first line of each test case contains a single integer n, which is the size of the grid. Like here, n equals 3, so it will be an n cross n grid cause n rows and n columns. So n is basically the side length of the square. So the character in the ith row and the jth column is dot if the cell is empty, or it is the type of token in the cell x or o. Like here it will be dot, here it will be dot, here it will be dot, here it will be x, here it will be x, and here it will be o. Yeah, so that's how it works. So it is guaranteed that not all cells are empty. Like at least one cell will have a token. And in the easy version, we'll be solving the easy version right now. The hard version, which has a pretty similar idea, will be a part of the mashup. So in the easy version, the character O doesn't appear in the input. So you can only have like grids of this type, this. Like these aren't possible because they have O. We aren't allowing O as an input in the easy version. The sum of n across all test cases does not exceed 300. So something like big of n square or maybe big of n cube, n square log n. So these are the kind of complexities we are looking for. So what we'll see is there exists an idea by which you can solve it in big of n square. So for that, we actually need some background before we can go to solving the problem. So what we need is the idea of coloring, which is a pretty common idea in mathematical problem solving. Ad hoc problems often involve ideas from mathematical problem solving. So this is one such idea which was used in this problem. So what you do in coloring is you take a grid like an n cross n or an m cross n grid, and you, yeah, I should not use n because I'm using it here. N cross n or a cross b grid. Yeah, so some grid of squares, and you color the cells of the grid according to the value of the coordinates modulo m's, where m is some positive integer. Like if you have colors c0, c1 up till cm minus 1, Then you color the cell I comma j with the color C I plus j percent m. That is the I plus j mod mth color. Like if you had m equals 3 and I and j were 2 and 2. So to color the cell, you would color the cell 2 comma 2 with 2 plus 2, which is 4 mod 1. That is the first color. Because 2 plus 2 is 4, 4 mod 1, 4 mod 3 is 1. So yeah, you would color 2 comma 2 with the first color, that is C1. The nice thing about such a coloring is that any m consecutive cells in a row or a column must contain each color exactly once. Now I'll be illustrating all these ideas with an example with a picture on the next page. So yeah, just be patient. I'll be repeating all that there also. So if you have any, like, let me just do it right now. So yeah, like here m equals 3. If you have like three consecutive cells like 1 2 3, then red occurs one, green occurs one, blue occurs one. So each color occurs exactly once. If you have three consecutive cells in a column, 1 2 3, then green occurs once, blue occurs once, red occurs once. So the nice thing about the coloring we've defined above is, like, if you have any m consecutive cells in a row or a column, then then these cells must contain each color exactly once. A very example of this is the chessboard coloring. You color cells with odd sum of coordinates black and cells with even sum of coordinates white, and it's called chessboard coloring because it looks like a chessboard. So yeah, coming back to the current problem, what we'll do is we will color the grid modulo 3. To make it more concrete, we will color the cell I comma j green if I plus j leaves a remainder 0 on division by 3, blue if the remainder is 1, and red if the remainder is 2. So you can see how the grid is colored. 1 comma 1 has remainder 2, so it is red, then this is green, then this is blue. And the reason we did this coloring is that it is motivated by the fact that for any winning configuration, three tokens which cause it to be winning lie on cells of different colors. Like for example, this is a winning configuration, and O. These are three tokens which cause the configuration to be winning. Then O lies on a green cell, this O lies on a blue cell, and this O lies on a red cell. So these three O's lie on cells of different colors, which is just this second bullet, this property that we mentioned. It is due to that these tokens will lie on cells of different colors. So the idea is, what if we can choose a color and change all the x's lying on cells of that color to o's? Like for example, we have this initial board. What if you say, suppose you change all the x's that lie on blue cells to o's, like you change this to o and you change this to o, then you cannot have any three tokens of the same type which are lying in three consecutive cells on a row or a column, because any three consecutive cells will have at least one blue cell. So the so that forces us to say that the type of token in the three consecutive cells has to be o, because if it is x, then we would have an x lying on a blue cell, and that would be a contradiction. But then we have o's only on blue cells, so it cannot be that the three cells have tokens of the type o. So basically, we won't be able to have three consecutive cells having tokens of the same type. So yeah, if we can choose a color like blue and change all the x's lying on cells of that color to O's, then we'd be done. Then the configuration will have to be a draw configuration due to this fact. But can we do this with less equal to k by floor of k by 3 operations? This is where generalized PHP comes to the rescue. And we can say that in a way the use of PHP means pigeonhole principle. So yeah, in a way we can say that the use of pigeonhole principle was motivated by the presence of this floor function. The three colors RGB are the boxes, and the KXs we are given initially are the objects. By generalized PHP, at least one of them contains less equal to floor k by 3 x's. Just change all of those x's to o's and we are done. Like for example, here k equals 7. We have two blue x's, two red x's, and three green x's. And floor of 7 by 3 is 2. And For example, blue has less equal to floor of 7 by 3, that is 2x's. So what we can do is we change all the blue x's to o's. Then we have used less equal to floor of 7 by 3 operations, and we have made the configuration a draw. So we see that this idea that we had, this will always work. So the time complexity of the solution is big of n square, because as you will see, I'll show you the implementation. You just need to traverse the n cross n grid twice. And this will easily pass for the given constraints, because the sum of n over all test cases was less equal to 300. Yeah, so let me open the code. So what I do is, this is just for input. You can ignore that here. So what we do is define the integer t, take input, and while while t is greater than 0, we call the function solve. I just like to put the solving part of the question in a different function and call that function for each test case. So what we do is we define the integer and take input into it, and then we define a vector of strings which basically represents our board. So each string in this vector will be of length n, and there will be n such strings. So for int I to n minus 1, you take input into board I, you store the ith string into the board. So now we basically have the whole board. So what we do is, now we count for each color how many x's are there on cells of that color. So we define a vector of size 3, which will basically store the number of x's of a certain color. So like color 0 will store the number of x's of color 0, colors 1 will store number of x's of color 1, and so on. So yeah, so you just traverse the whole grid. And if so, note that in this version of the problem, the tokens can only be of the x type initially. So if board I comma j is x, then you increment colors I plus j percent 3. So now what we want is some color for which the number of x's is less equal to floor of k by 3. Then note that the color with the smaller number of x's obviously has to satisfy this, because if there if there is an element less equal to floor of k by 3, then the minimum has to be less equal to floor of k by 3. So here what we do is we just find the index of the color with the minimum number of x's. Then what we want to do is we just want to change all x's of the type good color. So now what good color is, the color that holds the index such that number of x's of that color is minimum. So the color we were looking for is stored in good color. So now what we do is we change any x that is good colored to an O. So what we do is we just again traverse over the whole grid, and if board ij is x and the color is good color, you see out O. Otherwise you just see out whatever the board initially held, and then this gives the valid solution. You can, here I've already run it for some test cases. So for example, if you consider this test case for n equals 3, just a second. Yeah, so this is our test case. You have n equals 3, these are the x's. So what you'll note is, if you change the middle x to an O, like if you change this x to an O, this corresponds to color 1 plus 1, so color 2. So if you changed all x's that are of color 2 to O's, then you get this, and this code is outputting the correct grid that should be there after you made the changes. And I've already submitted it on Code Forces and it works. So I'll link the implementation and the problem in the resources we share after the session. So yeah, now you can, now I'll just look for any doubts that might be there. So yeah, you can ask me if there are any doubts. Otherwise, I guess we'll just end the session, because there is a Code Forces contest also starting from 6:30. Okay, so I guess there are no doubts. Then I guess I can then I guess we can end the session. Thank you so much for attending.